So, welcome everyone to one of the last sessions of CHES. We will have a session about physical unclonable functions. We have two talks in this session. The first one will be from Georg Maringer and Matthias Hiller from Fraunhofer Isaac. The talk is about information theoretic analysis of path-based temper protection. So Georg will be presenting. He is a graduate of TU Munich from PhD and now working at Fraunhofer Isaac. So please go ahead. Can we please shut the door? No. Just. Yeah, let's wait for a second. Apparently we are early, but we are on time.
Shall I still wait?
Let's wait a second.
Not just because they're only ringing. Because we only have
Well, I mean, let's start. Let's be on time.
Okay.
Yeah.
And be on time.
Okay, thank you.
Okay, so welcome everybody. Thanks for coming, even though it's the last day. So my name is Georg Maringer, and I will talk about some information theoretic analysis for physical clonable function-based temper. All right, so the solution to this problem that we are proposing at the Isaac is a path-based envelope, or I also call this thing often a foil. So what you want to do is you want to protect the cryptographic devices that you see inside the foil, so these chips here that potentially run some cryptographic algorithm from sidechannel attack. And you also want to derive a cryptographic key. Okay, so what serves as a path here? The path is basically composed of the capacitances that occur from this capacitive mesh here. So you see in red and blue electrode layers that are overlapping, and hence capacitances are formed. And okay, due to manufacturing variations, you get a key. And also, since this is the path, if you were to drill a hole or tear this foil off the devices to get inside with a probe to do measurements on the chip, well, then you would destroy the key as you destroy capacitances. So that's the basic principle. And there's also in black, as you can see here, shielding layers. So these prevent electromagnetic radiation from coming out to the outside that you could also maybe use in measurements. So what you want to do is you actually you want to prevent direct access, and also this makes it harder to do power side channels, and also laser fault injections are prevented. So the goal of this thing is basically to provide a security level of 128, 192, or 256 bits, which is basically the standard security levels, and I would say I measure it in the attack complexity of the attacker, corresponding to usual cryptography. And the goal of this talk is to find bounds on how many of these capacitive cells you need to achieve these goals. And there's two things. There's the security and also the reliability of the path. So the reason why you want to have these bounds is to get an idea of can such a design be feasible, right? If there were, I don't know, 10 billion capacitive cells required in the end, then potentially this is not so feasible. And then you really have to reconsider your design choices. Okay, so to go from scratch, the first thing that I want to do with this path is I want to enable key storage in a secure manner on my device. And okay, this is the first thing that you want to do. And the solution, as I said, are puffs. And what a puff is basically, in case you're not familiar yet, is it's basically a fingerprint of a device. So in some way, you can identify me by my fingerprint. And if I scan my own fingerprint several times, there's a tiny fluctuation because I tilt my finger maybe slightly on the reading device. But if some other person in the audience would use the fingerprint, then it's completely different from my fingerprint usually. And that's the same principle for a puff. Now, the thing here is that because the key is derived from this, and if I use a key in a cryptographic operation, the key has to be 100% exact, because even 1-bit fluctuations, for instance, as input to a hash function, will completely change the output. And hence error correction is used. Okay, and I also want to avoid sidechain attacks. As I mentioned, I go over this one quickly because I assume that everybody here is familiar with sidechain. Okay, so this is a quick recap on error correcting codes because this will be important later on. So for error correction, you consider a transmitter that wants to transmit a message in a reliable way to a sink. So imagine we have the message M, then you have the encoder that adds redundancy. Here, potentially errors are added to this code word. And at the receiver, you get this Y. This is the result of this. And if not too many symbols have been changed, then usually you can decode and get the code word back. And from the code word, you get the message. All right, so this is just a small example. Imagine this is the code word. I add this error here. This is this bit flip here. Then this is only one symbol changed. And if I designed my code in a smart way, then I should be able to. All right. Another concept are erasures. I mentioned this because it becomes important later on in our model. So here, imagine on top, I erase one symbol. So here, the recipient knows there was a symbol, but it's completely unclear to the receiver what this could have been. In a way, this is an easier thing compared to an error, because an error leads you into the wrong direction. Here, you just say, I don't know. And potentially, if you overdo it with your errors, then the outcome is something random, which has nothing to do with this. Or depending on the code design, it may also still be able to correct. In fact, what we later on want, that if you add erasures on top, that this cannot be corrected anymore. That's the goal later, but you will see. Okay, so I go briefly over helper data algorithms for puff design. So since a puff is the output is basically a physical quantity, you cannot really do coding over this, because coding implies that I can add redundancy in a controlled way. So I need to help myself by doing some code offset method here. And so in the first step, I take the puff response, which is this xn. This is basically n of these capacitive values. So this n also tells you how many cells you used here. Then what I need to do is I need to quantize it to do computations with this. And I also derive so-called helper data, which helps me later on in the reconstruction process when I want to get back my secret. So this one happens during manufacturing in some fab or something. And okay, what do I do? I take a random code word of the code that I want to use for error correction, and I add on top this quantized version of my puff, and I output w tilde n. This w tilde n and wn are public, so also the attacker has them. And then during reconstruction, what I need to do is I need to measure the puff again. This is signaled by this yn here. And I use this reconstruction helper data to get a more accurate estimate of what I had previously. And I subtract this value. And what I get then is the code word plus the difference between the two quantized measurements. And if this thing here is of small weight, so basically it's 0 in many positions and only in a couple not, then I can correctly decode and I can get back the secret also. Yeah. Now, what could be the problem with this? So there's two things. The first thing is, if you're not careful with the stuff that you published with this helper data, then this can leak information about the secret. And this is to be avoided. And for these analog paths, when I assume symmetric error distribution, symmetric noise, then this has been shown in these two works here. And how to do this such that no information is leaked. And I don't go into detail, but I use this. The other thing is that we are interested now is physical tampering. And here, basically, an aspect ratio for laser drilling is given. And what we say is, okay, we assume that the attacker has to drill a hole of at least 300 micrometers. And then he can insert a probe and measure. And he should have no success in getting any information about the key, because with the key he could decrypt the information that is stored in an encrypted manner somewhere, potentially inside this file also. Okay. Now this is the picture that we had before. This is just this enrollment and reconstruction. I put it together a bit to also introduce the attacker to you. For the attacker, he had to drill holes into this foil. So he destroyed certain parts. And since the attacker knows what he destroyed, at least I assume that he knows, which makes it stronger from our claim, he gets basically the same measurement as the legitimate user, but only after it has been passed through an erasure channel, erasing a certain amount of symbols, depending on the hole size. And then he does basically the same as this guy, just he got a worse estimate. And what you should be capable of doing in your code design is making sure that with this thing, he cannot recover the secret. While under normal use, without the holes inside this foil, everything should be working. Now the problem here is, as I've shown, that I use an error correcting code, and potentially this error correcting code will also be able to correct these erasures that the attacker inflicted by drilling the hole, and then he can just, if I'm not careful, he can just put the hole inside, and well, he will get the secret because he will just do the same measurement, and if this is not significant, what has been destroyed to my error correction, he has the same capability as the legitimate user. So you need to be careful here in this coding problem. And one solution for this is wiretap coding. And I'll go into more detail on this technique a bit later on the kind of channel model. Okay, so the basic problem that all this corresponds to is secret sharing using common randomness. And this is a problem that has been studied by the information theory community quite a bit, I would say. Notable works are by, for instance, Alswede and Maurer. They analyzed this in an asymptotic setting. So what is done here is you basically have a joint source with three outputs, A, B, and E. And so you imagine that you sample this thing n times, and you take the A shares and give them to Alice, give the B shares to Bob, and give the E shares to the eavesdropper Eve. And the goal of this scenario is that Alice and Bob use a public communication channel, so Eve eavesdrops these pi's and psi's here, and they agree on a key, and leave Eve oblivious about the key, of course. So this is what is done, and in the end, they put out a key, Ka and Kb, and those shall be equivalent. Now, how does this correspond to our path scenario? here you basically also have a joint probability source with S, which is the enrollment measurement, S tilde, the reconstruction measurement of the legitimate user, and SD tilde, which is the eavesdropper's measurement. And the helper data is basically the stuff that you put over the public communication channel. So one thing that is different here compared to the generic scenario is that the communication can only be one way. Remember before you could communicate to Alice and Bob back and forth, but here you have to live with one-way communication, which asymptotically, Alsveda has shown, doesn't make a difference. You get the same rates. In finite length, there is difference. Not proven, but there exists no protocol in one way that achieves the optimum. Okay. Now here a little bit more formal about the same problem. So you want 4 things to happen, and you call a rate, which is basically code rate, achievable if for every tiny epsilon, the probability that the keys are not matching is upper bounded by this epsilon. You have, so this is just the reliability. Then what you want is that the leakage between the stuff that you share over the public channel and the measurement that Eve is doing about the secret is as small as possible. So this is upper bounded by epsilon, so it's just a leakage. You want the key to have large entropy, basically larger than this rate. And you also want the key to be uniform over the key space. And this is the 4th condition. So here's just math, but basically this tells you what it should be. And it has been shown by Alsveda and Caesar that the maximal rate that you can achieve asymptotically can be computed by subtracting these 2 mutual information. So the mutual information between A and B minus the mutual information between A and E. And this also makes some sense because, okay, if the channel to Eve was equal to Bob, then of course you can do nothing because you have 0 advantage. And the more this advantage increases, the higher rate you can get. Intuitively, this makes some sense. So now we come to this wiretap channel model. And in a wiretap channel, Alice wants to transmit a message to Bob using an encoder. And what she does is she uses the fact that her channel to Bob is of better quality than her channel to Eve. And this you can use, and you get information theoretic security with this, even. That's stronger notion than cryptographic security. Okay, so this is basically the generic setup. And if I put this into context with our puff problem, then you again have, this is the randomness that chooses the code word in the fuzzy extractor. Get this code word, and here you get as output the helper data and the reconstruction measurement, and Bob has to decode. And here for Eve, you only get this degraded version, and also the helper data, since this is public. And you want to make Bob understand everything and leave Eve completely oblivious about what you want to communicate, so about this R. Okay. Now, there's 2 things that are important in finite length, because we are always interested in finite length. Asymptotics are nice for a first estimate, but I want more. I want to plug in a specific n, which corresponds to the block length, and I want reliability, which is this condition. So here, the probability that Bob cannot decode the message shall be upper bounded by epsilon. And this is the security condition. So what you have here is a distance between the joint distribution of the message and the eavesdropper output. So it's the distance between the joint distribution and the 2 marginal distributions. And I mean, if stuff is independent, then the joint distribution is equal to this product. So if this one is small, then we are good. And we take here the security level that we want. So for instance, delta 2 to the minus 128. All right. This is the bounds on the finite length rate of the wiretap coding problem. And while this may look really complicated at first glance, I want to introduce the terms a little bit such that you get an idea what's happening here. So this was the asymptotic rate that I've shown you before. And here you have correction terms for finite length n. So this one is a first estimate, but you get more precise here. So if you look at those things, as n goes to infinity, all these terms are vanishing. What you have here are two channel dispersion terms, and these are these two constants here, v1, v2, and vc. And the important part here is that they depend on the channel, yeah, but they do not depend on the block length, the constants here. They are then scaled with the block length, and a square root is taken. So those are the second order terms, and if you also integrate those, you get a more precise estimate of what comes out. Now, what do we get in the end? We get bounds on these rates that you can achieve, and if I have the rate and I multiply it by my length, I get the dimension and the code dimension. And the code dimension, of course, has to be larger than the security level, because otherwise you could just brute force, and if your brute force then has a lower complexity of your desired compared to your desired security level, so that's nonsense, of course. So what we get here is, for instance, if we take a quantizer at the input with 1 bit, so 2 symbols, we get an achievability for reliability 10 to the minus 6 and an erasure probability of 0.18, which corresponds to our 300 micrometer hole that we assumed in the beginning. We get an achievability of roughly 2,000. So it means if I have 2,000 of these capacitive cells, then I should be successful in achieving the security level and the reliability that I want. And also, it's shown that you cannot do it with less than 1,000 cells for binary. And this is just for different quantization levels, so it fluctuates. And here are the results in red and green for 256-bit and 192-bit security. Okay, so the final thing is what you can do with the converse bound, which basically states you cannot achieve it with less than a certain amount of cells. You can take existing schemes and you can check whether they fulfill the converse bound. And if they don't, you know there's a flaw in the security analysis. So this is what happened here in this work, and I just wanted to mention this because so one of two things then has to occur. Either the helper data is leaking, or the error correcting code can be exploited by the attacker. Both things are bad, so you need to be aware of that. Okay, so what you should take away from this talk is that finite block length information theoretic tools can be useful to provide these bounds. If you go to finite length, this gives you, it's quite practical. In tamper protection, you need to be aware that error correction can help the legitimate user and the attacker if you're not careful. And wild-type coding can be a solution. And as I've shown, just some results, about 2,000 capacitive cells are sufficient for reaching 128-bit security, and that the converse bound can be helpful to analyze existing schemes. So thanks very much for listening.
Thank you. Thank you. Thank you very much for the nice talk. Do we have any questions from the audience?
I have a question on your attack model, but it might go to the previous reference, which I've already read. But you said that a hole destroys two electrodes, and therefore you destroy 18% of the capacitance values.
Mm-hmm.
It's part of your assumption. If that's not true, right, if I could drill a hole and maybe avoid the electrodes partially, then what happens if I have a more effective attack than what you assumed?
Okay, then you have a different erasure probability. If you're not this, so the thing is, there's some matrix thing, and if you destroy one, then you destroy basically a column in a row in this matrix thing. So by destroying one cell, you actually destroy many in the measurement. And if you can drill a hole that is smaller, such that you drill between the mesh, well, of course you succeeded because I cannot detect it.
Yes.
So the assumption is that you so I choose the aspect ratio of the drilling in a way, and I take a conservative assumption. If you can then in the end drill a smaller hole, of course I lost. It's clear.
Or repair it, which could be possible
if you can properly repair it, yes, I'm also lost. So you can fine tune the model more and see what it does. Yeah.
We may have time for another quick question. I have a quick question about, so this 2000 capacitive cells, it is actually what you also write in the paper, 459 PUF cells using 3-bit quantization. So you mean that, right? So to reach the same. Because it also says like 128
Okay, here there's only 1-bit quantization assumed.
Okay.
But you can, if you go back like this, 3-bit quantization is here. So here you would say, okay, I can do it with,
it's
I don't know,
less,
1500 or something.
Okay.
And you can definitely not do it with less than
1,000.
400. No, I mean
Yeah.
here.
Okay.
Maybe 500, 400, whatever.
Okay.
I don't know the numbers exactly.
Okay.
In the paper there's a table. You don't only get.
Okay. Now I see that. Okay. Thank you very much. Let's. Thank the speaker again.
Thank you.
Now we will have our next talk. So this time we will be hearing about protection of oscillator-based PUFs against side channel analysis by random interruption. So this is a joint work of Holger Mandry, Jonas Ruchti, Julius Nowakowski, Michael Pell, and Marius Ortmans. So Jonas from TU Munich will be giving the presentation.
Yeah, thank you very much for the nice introduction. I will be presenting that on behalf of my co-authors from both University of Ulm and Technical University of Munich. And this is a side channel countermeasure. So my main focus will be on the actual measurements we did in this presentation, and I will only leave a few words about the PUF performance after that. But before that, let's look at the general concept, what we are trying to achieve. So we want some sort of key storage using hardware variations, and one way of achieving that is using a ring oscillator. So we add a few delay gates in a combinational loop, and the actual delay is going to depend on the exact makeup and hardware variations of the transistors in these delay gates. So if we build a loop, the oscillation frequency will depend on that. Typically, we add some AND gate or NAND gate in this case, enable the oscillator for a fixed amount of time, count the number of rising edges, and then we get a raw PUF response, some estimate for the frequency. Of course, we can tweak that a bit, enable it for longer, so we get a better estimate of the frequency. Mostly, we will use multiple oscillators so that we can compensate for temperature effects, and then we take the difference of these estimated frequencies. And in the simplest case, we just pick which of two oscillators is larger. That gives us one single bit of secret information depending on hardware intrinsics. If you want to do more, we can also use the magnitude of that difference. So you can use that for higher order quantization, more than 1 bit per pair of oscillators, or we can use it for additional reliability, like the 2-metric helper data scheme. We can also add some challenge input to our delay cells. So in this case, we can in each position have something like a multiplexer, which has an upper and a lower path. which are nominally the same, but depending on the challenge, actually different due to hardware variations. And then we get a loop puff. So we get multiple different frequencies from a single ring oscillator. So the great part of this construction is that the frequency is your secret, so that is easy to measure. But the drawback is that the frequency is your secret and you have side channel leakage because that frequency can be easily observed from a power side channel measurement, for example. We do have some existing countermeasures against that. So if we only have sign-based quantization, then that is pretty easy. You can essentially do masking, swap the order of challenge evaluations, or just evaluate multiple ring oscillators in parallel, and then you cannot longer tell the sign at all. So you're completely secure there. If you want the magnitude to be protected, that is more difficult, because you can think of like you do a spectrum of your power side channel measurement, you get 2 peaks, you can measure the distance of these 2 peaks. One countermeasure that exists is the interleaved challenge loop puff, but that switches the easy frequency measurement to a time domain measurement, needs more complicated hardware, and has a up-down counter in it that can leak as well. So our goal for this work is, can we build a simpler countermeasure that still protects the magnitude of the frequency difference? To do that, we start from the simple ring oscillator that is, when enabled, going to produce some sort of frequency. Then we insert at each point after each delay gate, we insert a latch, and that latch can be switched from transparent, so just a wire, to store, so we keep the current state of the oscillator. And we call that an interrupt signal because it kind of stops the signal if we set it high, and if it is low, then the latches are as if they are not there and the oscillator runs. So let's apply some sort of random signal to the interrupt signal, and then we see that each of the orange parts should be an interruption in the signal, and we see that, okay, actually then the oscillation is kind of paused. We don't get any stage transitions while the latches are set to store the current state. You can think of it like a odd game of musical chairs. So we get 1 chair for each latch. We have 1 guy who is running around in a circle. That would be the rising edge. And then we randomly stop the music, and the guy has to sit down, and then the music restarts, and he's to go around in circles again. And our claim here is that if we start and stop the music frequently and randomly, then it is very hard to tell how fast the guy is going around from the sound of his footsteps. Again, we can still use a loop puff. So for the actual evaluation, we will use challenge inputs for the individual delay cells, just so that we get more different frequencies from the same loop. All right, let's see if that works. We start by doing just the basic experiment. So we use the same design where we have, as you can see in the block diagram, the black part is completely usual. We get a number of loops in parallel. In our case, we have a single counter per loop, and then we add to that an interrupt signal, so latches in each loop, a common interrupt signal which is generated by a PRNG, whose seed we can control and whose clock frequency we can control, so how fast the interrupt signal changes. For our evaluation, we implement that on an FPGA and conduct power side channel measurements, and we also choose a pretty powerful attacker, so we assume that 1 single loop is running for the attack on the loop frequency. The loop is also rather long, so that's 64 stages and gives us a rather low frequency, just so that we can have a lot of oversampling. So we can see the difference between 10 megahertz of the loop frequency and 5 gigasamples. We want to get a lot of information in the attacker's hands, and we can then also average some traces where we have a constant interrupt generator seed. So that also is a stronger assumption than what we would have in the reality. Later, you will also see a different design which has a lot of loops in parallel, which are shorter, because we will also take a look at the interrupt signal, and that turns out to be a stronger assumption in this case. So base case is we don't use the interrupt at all, so we just set the latches constantly to transparent, and then we have a regular loop path. So that is useful to cross-check that the actual baseline attack still works. So what we do here is we collect 10 traces per challenge, do an FFT on each trace, average all of these FFTs, and then we look for peaks in the spectrum. And what you can see, so in the background is the actual measured spectrum. The lines in the foreground are like a smoothing applied to that, so we can more easily see variations down in the measurement noise. And what you can see, like 2 exemplary challenges, we get a shift in peak, and that difference in these peak frequencies is exactly our secret. So baseline attack without any protections absolutely works. Let's turn the interrupt signal on. So in this case, I used a clock frequency of 20 megahertz for the interrupt generator, and the most dramatic change we see at the beginning is that we get that large lump at the lower frequencies. That is basically the random signal generated by the interrupt signal itself. We also don't see the regularly spaced peaks at the oscillation frequency and the harmonics anymore, so that is kind of good. However, we still see one small bump somewhere here. That is at a different frequency than the second harmonic we saw before. So that is a mixing product of the fastest frequency the interrupt signal can change at 10 megahertz and the baseline loop frequency of 9.3 megahertz. And that still contains information. So using that, we can still conduct an attack. It is a bit weaker, so we only saw like 70% attack accuracy here. As you can also see, these signals are a bit smaller. So let's try to increase the interrupt frequency, and in this case, we don't see any information anymore. So with a high enough interrupt frequency, we are side channel secure in this case. But still, this is a very simple attack. We just collect traces, we do an FFT, and then we look for peaks. Can we be smarter? So let's assume that this is our power trace, and let's assume for a second that our attacker knows the interrupt signal. So we can, for a second, look at all the parts where the interrupt signal is low. So that's the parts where the loop is actually running. And we kind of construct a virtual trace. So we stick all of these together, we cut all the parts out where the loop was interrupted, and we make a virtual new trace, and then we frequency transform that. And if we do that, we again get a working attack. So that is a very small portion of the spectrum, again with some smoothing on top, and what you can see is that you can clearly see that, okay, there are peaks for 3 exemplary challenges here, and these peaks correspond well to the orange lines, which are the on-chip measured frequencies, or the actual secret where we would expect them to be. That is, in our examples, that is over 90% accurate, that attack, and basically says to us, okay, we cannot use a constant PRNG seed. So the interrupt signal really needs to be random, and we should not let the attacker know this. We also found out that the attacker really needs a good representation and good knowledge of the interrupt signal. So if you get 1% of the interrupt bits wrong, then we already see a severe impact, and at 2%, it basically gets impossible at all to carry out this attack. So also it's kind of intuitive, because at any point, if you get a interrupt portion wrong, then you get kind of an accumulated phase error for the remainder of your whole signal, and get enough wrong, and there's not enough signal left to mount the attack on. Okay, so we now know that we should not let our attacker gain access to the interrupt signal. We just use a PRNG with a truly random seed, for example. But maybe we can do a higher order attack. So at the first stage, extract the interrupt signal, use that to do this attack, and then extract the secret. Let's see if that is possible. And here I'm going to use the second design, which has many loops in parallel. And what you see in this plot is just a time domain power side channel trace in the background. So every time there's a blue square, the loop is interrupted, and every time it's white, it is running. And the orange trace is a moving average over the average over 320 power traces. And what you can see is that we see a dip in the orange trace anytime we switch from on to off or off to on. So for portions where we have a longer period where the loop is unchanging, we get the sort of recovery effect. And for portions where we see many changes, we see a dip each time. So it is reasonable to say, okay, you might be able to do a simple power analysis attack where you just visually extract these interrupt bits and then do the second order attack. Our simple protection, or at least first the root cause for that, is we have one interrupt signal, we have many loops, and each loop has a number of latches, so we have a huge fan out. So every time the interrupt signal changes, we see a switch over of many gates, and that gives us a large power draw, and we see that in the side channel. So simple power countermeasure would be something like a balancing. So we actually split the interrupt for our whole loops into two different domains, and we build a simple circuit such that one of the interrupt lines changes whenever the other doesn't. So in any clock cycle of the interrupt clock, exactly one of these two lines changes, so we get a balanced overall effect. And in this case, you now see that we have like two different shaded overlaid backgrounds for the interrupt signal. These are the two different interrupt signals. We get exactly one change in each clock cycle, and therefore we don't see something in the power side channel anymore. Again, this is a constant PRNG seed, so in a realistic setting, you would not be able to collect 320 traces with the same interrupt signal, because you would change that for every evaluation. So while this is not a perfect or like theoretically secure countermeasure, it will be good enough, because based on that, it will be no way of extracting the interrupt signal with the accuracy that is required for the second order attack to work. That covers the side channel experiments, but we still need to ascertain that we don't have a too negative impact on the puff performance. And the one thing I'm going to look at in this presentation is the bit error rate, because that is the most intuitively impacted thing here. After all, I said in the beginning, if you measure for longer, you get a more accurate representation or accurate estimate of the oscillator frequency, and we kind of cut our measurement time in half here, because half of the time the loop is going to be disabled. Also, we might see additional metastability, because each time we switch over from like interrupted to running to interrupted, we might see instability in the latches. And we also might have problems because we only have a limited number of seats for a musical chairs game, and get some kind of phase quantization. And indeed, we see some effect when we measure very short. So what you see in this plot is the evaluation time, how long the runtime is on the x-axis, in relation to the bit error rate. And again, we use both modes of our puff. So we use a continuous mode where we don't use the interrupt signal as a continuous line, and the dashed line as the interrupted operation. And we compare both in this plot, blue just sign-based, and orange to metric helper data scheme where we actually need the magnitude. And what you can see is, okay, for small evaluation time we have indeed an effect, but that kind of tapers out. So if we use a longer evaluation time, we don't really see that much of a difference between interrupted and continuous operation anymore. So our claim here is that basically we do get a manageable impact on the performance of the puff by including that countermeasure. All right, to conclude already, we have shown that we can use random interruption of a oscillator-based puff. So that is like a ring oscillator puff, a loop puff, but likely also something like a taro puff, and as a countermeasure against side channels. That protects us against simple attacks, and in case we also include some simple balancing-based countermeasures for the interrupt signal that also protects us against two-stage attacks, like I've shown before. The overhead is really minimal. Basically, you need a PRNG, and you need a latch for each delay element. If you are doing this on an FPGA, the latch basically comes for free because you have one in the logic block you are going to use for your delay element anyway, and the impact on the performance is manageable as well. In the paper, we have some more sections on doing this mathematically and in simulations. So I've just shown you the actual measurements we did on this, but you will find some more on that in the paper. We also take a look at different ways we can build these latches in the FPGA, and you will also find more than just bit error rate, so full puff metrics over voltage and temperature in the paper. What is still to do? We actually need some more accurate simulation on the occurring signals, because even if we take effects like jitter and phase quantization into account, we see some a bit different effects in reality, like the mixing product I've shown you, than we could predict in the simulation. So that kind of needs more work to actually do a more accurate simulation here. And still, I've shown you two different exemplary interrupt frequencies, and what the actual optimum is also still open, because you can intuitively tell, okay, it's not zero, you wouldn't have interrupt at all, and it's not infinite, because that would not protect you anyway either. But somewhere in between gotta be the optimum, and where exactly that is, we don't know yet. And that already concludes my presentation. Thank you for sticking around.
Thank you very much for the nice talk. Do you have any question?
Did you consider the side channel analysis having a CNN, because a convolutional neural network would potentially detect features from your interrupt-based countermeasure?
I did not use any machine learning-based analysis. I had a few short experiments with wavelet-based transformations, because those would also allow me to figure out like small time-based only one, and would be less probably affected by phase differences between the different parts, like an FFT would be. I did not have any success with these. What's maybe also interesting is that in general, the interrupt is very often faster than the actual oscillation frequency. So the goal is that we it's random, we will get some full periods every now and then, but very rarely. So that would limit naturally the success probability of such an attack. But I did not try a CNN. Good suggestion. Yeah.
Right. Thank you for the interesting talk. I was wondering which PRNG are you using and why is the seed only 32 bits?
Good point. So for this work, we just use an LFSR. In reality, you would probably use a real PRNG because you could attack the LFSR, but we did not consider that as a point of attack, so we just use a simple one here.
Okay, and if I can ask a second question, I was wondering about the robustness of your second order attack.
Yeah.
Let's say I try to do this attack and I made some mistakes. I accidentally include some cycles where your interrupt signal is active. I assume I can still do the attack with maybe less probability. So I was just wondering how wrong can I be in order to still be successful?
So I did some experiments where I just randomly flipped some bits in the interrupt signal, and at 1% you get an impact you really notice. So you see, I don't have the number right now, but you see really an impact on the accuracy. At 2% it basically becomes impossible. Right. Below that, it still works.
All right, thank you very much.
Any other questions? So for FPGA, it's manageable overhead. For ASIC, have you ever estimated anything?
We don't have any estimates, but okay. I mean, for ASICs, you don't get the latches for free.
Yeah, okay, so basically we can roughly calculate then as a guess. Okay. Okay, so this actually concludes our session. This was the last talk. Thanks again for your talk. And with this, I would like to thank you also for attending. And this concludes the PUF session for CHES.